Mars will kill you. They sold you a dream. Elon Musk, NASA, science fiction. Everyone promised you Mars, but here's what they didn't tell you. Mars is actively trying to kill you in ways we're only beginning to understand. And the more we learn, the worse it gets. This isn't about technology catching up. This is about physics, biology, and a planet fundamentally incompatible with human life. And here is a question. If you could ask the universe one question and get a definitive answer, what would it be? Let us know in the comments. I will pin the most creative answer. Now let's begin. When we dream about Mars, we often imagine gleaming domes sheltering thriving communities, gardens growing under artificial suns, children born on another world looking up at two moons. But reality doesn't care about our dreams. The cosmos operates on principles far older and more powerful than human ambition, and Mars, despite being our closest potentially habitable neighbor, presents obstacles that aren't just difficult, they might be insurmountable. The story begins 4 billion years ago, when Mars was a dramatically different world. Evidence from missions like NASA's Curiosity and Perseverance rovers tells us that ancient Mars possessed something our red neighbor lacks today: a protective magnetic field. This invisible shield, generated by churning molten iron in the planet's core, wrapped around Mars like an embrace, deflecting the relentless solar wind and deadly cosmic radiation. Rivers carved through valleys, water pooled in vast lakes, and the atmosphere was thick enough to maintain liquid water on the surface. If a life ever had a chance on Mars, it was during this golden age. But then, catastrophe struck. Mars is significantly smaller than Earth, roughly half our diameter with only about 11% of our mass. This seemingly minor detail sealed the planet's fate. Smaller planets cool faster because they have less internal heat to sustain geological activity. As Mars's interior gradually cooled, the dynamo that generated its magnetic field sputtered and died. Scientists estimate this happened around 3.5 to 4 billion years ago, relatively early in the planet's history. The consequences were apocalyptic. Without a magnetic field, the solar wind, a relentless stream of charged particles flowing from the sun at speeds exceeding 1 million miles per hour, began stripping away Mars's atmosphere like wind peeling paint from an old house. This wasn't a quick process, but on geological timescales, it was devastating. Over millions of years, the atmospheric pressure plummeted. Water evaporated or froze into the soil. The planet transformed from a world that might have harbored life into the frozen desert we observe today. The Mars Atmosphere and Volatile Evolution mission, known as MAVEN, launched by NASA in 2013, has been studying this atmospheric loss in real time. The spacecraft orbits Mars, measuring how the solar wind continues to strip away approximately 100 tons of atmosphere every single day. Think about that for a moment. Every day, even now, Mars loses the equivalent mass of about 50 cars worth of its precious thin atmosphere to space. This ongoing hemorrhage means that even if we somehow added atmosphere to Mars artificially, it would gradually leak away without a magnetic field to protect it. This brings us to the first fundamental problem for human colonization: radiation. Here on Earth, we're protected by two magnificent shields. Our planet's magnetic field extends tens of thousands of miles into space, creating a region called the magnetosphere that deflects most harmful cosmic rays and solar particles. Additionally, our thick atmosphere, which has a surface pressure 14 7/10 times greater than Mars, absorbs radiation that manages to penetrate the magnetosphere. Together, these shields reduce our radiation exposure to levels life has adapted to over billions of years. Mars offers neither protection. The planet's atmospheric pressure is less than 1% of Earth's, so thin that it's essentially a vacuum. Standing on Mars's surface, you're exposed to two primary types of space radiation: galactic cosmic rays and solar particle events. Galactic cosmic rays are atomic nuclei, mostly protons with some helium and heavier elements, accelerated to nearly the speed of light by supernova explosions and other violent cosmic events. These particles carry enormous energy, some exceeding 50 billion electron volts. They bombard Mars constantly, penetrating rock and ice with ease. Solar particle events, on the other hand, come from our own Sun during massive eruptions called coronal mass ejections. During these events, the Sun hurls billions of tons of charged particles into space at millions of miles per hour. When these particles reach Mars, they deliver intense radiation doses that can increase surface radiation levels by as much as 50 times normal background levels within hours. According to recent studies published in late 2025, including research from the Harbin Institute of Technology and data from NASA's Mars Science Laboratory Radiation Assessment Detector, the RADI instrument aboard the Curiosity rover, astronauts on Mars's surface would receive approximately 0.6 to 0.7 millisieverts of radiation per day. That might sound abstract, so let me put it in perspective. A typical chest X-ray delivers about 0.1 millisieverts. Living on Mars, you'd receive the equivalent of 6 to 7 chest X-rays every single day. During the journey to Mars, which takes roughly 6 to 9 months depending on planetary alignment, the radiation exposure becomes even more severe. Without any planetary shielding whatsoever, astronauts in transit would face approximately 1.3 to 2 millisieverts per day, double the surface dose. This means a round trip to Mars, including surface time, could expose astronauts to between 600 and 1,000 millisieverts of radiation, depending on mission duration and solar activity. Now here's where it gets truly concerning. NASA currently sets career limits for astronauts based on age and sex, designed to keep their lifetime excess cancer risk below 3%. For most astronauts, this limit ranges from 600 to 1,000 millisieverts, meaning a single Mars mission could consume or exceed an astronaut's entire career radiation allowance. But cancer isn't the only concern. Recent research, including work highlighted in Nature's journal NPJ Microgravity in 2020, identifies radiation as one of the red risks, the highest priority health threats for Mars missions. If you've been enjoying this exploration of Mars's deadly nature and want to understand more about the extreme environment of space itself, make sure to subscribe to this channel and give this video a like. Your support is the biggest fuel to keep this channel going. The biological effects of cosmic radiation extend far beyond cancer risk. High-energy particles don't just damage DNA, they create tracks of ionization through tissues, destroying multiple cells along their path. When these particles strike the brain, they can damage neurons and neural connections, potentially causing cognitive impairment, memory problems, and behavioral changes. Studies on mice exposed to cosmic radiation simulations show deficits in spatial learning and memory that persist long after exposure ends. Imagine colonists on Mars gradually losing mental sharpness, struggling with decision-making and problem-solving in an environment where mistakes can be fatal. Cardiovascular effects present another insidious danger. Radiation damages the inner lining of blood vessels, promoting inflammation and atherosclerosis, the buildup of plaques that can lead to heart attacks and strokes. Research on atomic bomb survivors and radiation therapy patients demonstrates that radiation exposure significantly increases cardiovascular disease risk, and this risk appears to persist for decades. Mars colonists could face elevated heart disease risk for the rest of their lives, even after returning to Earth. The eyes are particularly vulnerable. Cosmic ray particles passing through the retina create flashes of light called phosphins. Astronauts on Apollo missions reported seeing these cosmic fireflies even with their eyes closed. More seriously, radiation can accelerate cataract formation, potentially leaving long-term Mars residents with impaired vision. Combined with other vision problems associated with spaceflight, this creates concerning implications for quality of life. Now you might be thinking, can't we just build better radiation shielding? This is where physics becomes our enemy. Traditional radiation protection uses mass, thick layers of material to absorb or deflect particles. On Earth, this works wonderfully. Nuclear facilities use meters of concrete. Space stations in low Earth orbit benefit from Earth's magnetic field for most protection. But Mars offers no such luxury. The harsh reality is that truly effective radiation shielding against galactic cosmic rays would need to be extraordinarily massive. Hydrogen-rich materials like water or polyethylene work best because lightweight nuclei don't fragment as much when struck by cosmic rays. But we're talking about needing several meters of such material surrounding every habitat. Imagine trying to launch enough shielding material from Earth to protect a Mars base. The mass requirements would be astronomical, perhaps literally impossible with current propulsion technology. Some proposals suggest using Martian soil, called regolith, to bury habitats underground. This approach has merit. Several meters of regolith would provide significant radiation protection. The European Space Agency and others have tested concepts for 3D printing habitats using Martian soil mixed with binding agents. Underground or heavily shielded habitats could reduce radiation exposure to more manageable levels. But here's the cruel irony: the more we shield ourselves from radiation, the more we create a different problem. We're not just protecting ourselves, we're building elaborate prisons. Imagine living your entire existence underground or in cramped, heavily shielded modules, knowing that stepping outside means bathing in lethal radiation. The psychological toll of such confinement brings us to another critical challenge: the mental health crisis waiting to happen on Mars. Human beings evolved in specific environmental conditions. We're adapted to Earth's gravity, its day-night cycle, its atmospheric pressure, and crucially, its connection to nature and open spaces. Confining people in cramped, sealed habitats for years, possibly decades, creates profound psychological stresses that we're only beginning to understand through analog studies and experiences aboard the International Space Station. NASA's Human Research Program identifies behavioral health and performance as one of the 4 highest priority red risks for Mars missions. The challenges are staggering. Unlike astronauts on the ISS who can see Earth outside their windows, speak with loved ones in real time, and no rescue is theoretically possible, Mars colonists would face complete isolation. Communication delays between Earth and Mars range from 4 to 24 minutes one way, depending on planetary positions. A simple conversation becomes impossible. Need advice during an emergency? You'll wait up to 48 minutes for a response, an eternity when lives hang in balance. The psychological research is sobering. Studies from Antarctic research stations, submarine missions, and isolation experiments reveal that even highly trained, psychologically screened individuals experience significant mental health challenges during long-duration isolation. Depression, anxiety, interpersonal conflicts, and cognitive decline all increase with mission duration and isolation severity. The Mars 500 project, a simulation where 6 crew members spent 520 days in an isolated facility in Moscow, documented sleep disturbances, motivational changes, and performance decrements, despite the participants knowing they could leave if absolutely necessary. Now imagine the same scenario, but you genuinely cannot leave. You're 225 million kilometers from Earth, at your farthest. There is no evacuation, there is no going home on a whim. The Martian environment itself is actively trying to kill you every moment. The psychological pressure would be immense, unrelenting, and unprecedented in human experience. The isolation compounds when you consider group dynamics. Small, isolated groups develop unique social pressures, Conflicts that would be minor annoyances on Earth, someone chewing loudly, different cleanliness standards, personality clashes, become magnified when you cannot escape the person bothering you. You'll see the same handful of faces every single day for years. Historical accounts from polar expeditions and submarine patrols document how such proximity can lead to intense interpersonal tensions, sometimes erupting into violence or psychological breakdowns. Adding another layer of complexity, the crews would need to be highly diverse in skills: engineers, biologists, physicians, geologists, technicians, meaning people with very different backgrounds, thinking styles, and communication patterns forced into intimate proximity. The potential for misunderstanding and conflict multiplies, and unlike on Earth, where you can quit a job or move to a different city, Mars colonists would be locked into their situation for years. The sensory deprivation aspect cannot be overstated. Mars lacks the sensory richness of Earth: no wind rustling through trees, no birds singing, no rain pattering on windows, no ocean waves. The sky is a butterscotch haze rather than brilliant blue. The landscape, while initially striking, is monotonous. Endless rocks and dust in shades of red and brown, unchanging for hundreds of kilometers in every direction. Everything smells like regolith, a fine, toxic dust that infiltrates everything. Every meal is recycled or reconstituted. Every sound is mechanical, artificial. Humans are biologically wired for natural environments. Research in environmental psychology demonstrates that exposure to nature, even just viewing images of natural landscapes, reduces stress, improves mood, and enhances cognitive function. The Japanese practice of forest bathing, or Shinrin-yoku, has documented health benefits. Mars offers none of this. The chronic absence of natural stimuli could create a low-grade psychological malaise that persists throughout colonists' lives. Speaking of the dust, let's talk about another insidious danger: perchlorate. This chemical compound, discovered on Mars by the Phoenix lander in 2008 and confirmed by multiple subsequent missions, saturates Martian soil at concentrations around 0.5% by weight. That might sound minimal, but perchlorate is toxic to humans, particularly affecting thyroid function. The thyroid gland mistakenly absorbs perchlorate instead of iodine, disrupting hormone production and potentially causing metabolic problems, developmental issues, and neurological effects. The dust itself is incredibly fine, much finer than Earth sand, and electrostatically charged, causing it to cling to everything. Apollo astronauts discovered lunar dust posed serious problems, irritating eyes and lungs, damaging equipment, and proving nearly impossible to keep out of habitats. Martian dust would be worse. It would coat solar panels, reducing power generation. It would abrade mechanical seals and joints, and critically, it would carry perchlorate directly into habitats and lungs. Inhaling perchlorate-contaminated dust repeatedly over months or years could lead to chronic thyroid dysfunction. Without a functioning thyroid, your metabolism collapses. You'd experience fatigue, weight changes, depression, cognitive impairment, and numerous other health problems. While thyroid hormone replacement therapy exists, imagine depending on a pharmaceutical supply chain stretching 225 million kilometers. If that supply is interrupted through mechanical failure, launch delays, or any of countless potential disruptions, colonists face serious health crises. If you're finding this deep dive into Mars's hostile environment fascinating and want to explore more about the extreme nature of space, I highly recommend watching my video called "The Terrifying Truth About How Cold Space Really Is." It explores another fundamental challenge to human survival beyond Earth: the absolute cold of the cosmos and what it means for human biology. Check it out after this one. The link is in the description and on the card above. But for now, let's continue examining Mars's lethal characteristics. beyond perchlorate, the dust may harbor other dangers we haven't fully characterized. Mars is chemically different from Earth. The regolith contains oxidizing compounds that could react with organic materials, potentially creating harmful chemicals when exposed to water or biological systems. We won't fully understand these risks until humans actually live there long term, making early colonists involuntary guinea pigs in a massive toxicology experiment. Now let's address the atmosphere more directly, or rather, the lack thereof. Mars's atmospheric pressure averages around 610 pascals compared to Earth's 101,325 pascals. This is less than 1% of Earth's pressure, roughly equivalent to the atmospheric pressure at an altitude of 35 kilometers above Earth's surface, far above the Armstrong limit, the altitude at which water boils at human body temperature. The implications are immediately deadly. Without a pressurized suit, exposure to Mars's atmosphere would cause the water in your tissues to vaporize. Your blood wouldn't boil exactly as it's contained within blood vessels, but the water in your mouth, eyes, and respiratory tract would bubble and evaporate within seconds. You'd lose consciousness within 15 seconds due to oxygen deprivation. Death would follow in 1 to 2 minutes. There is zero margin for error. A suit puncture, a habitat breach, an airlock malfunction, any of these means almost certain death unless remedied within seconds. This creates an existence where you're perpetually dependent on technology functioning perfectly. Every moment outside requires a complex life support system working flawlessly. Every seal must hold, every valve must operate correctly, every sensor must provide accurate readings. The redundancy requirements are staggering, and even with multiple backup systems, the probability of fatal equipment failure over years of exposure increases substantially. Think about the psychological weight of that constant danger. Every time you need to venture outside to repair equipment, gather samples, tend external systems, you're one malfunction away from a horrible death. The chronic stress of living under such conditions, where a simple mistake or equipment failure means suffocation or explosive decompression, would exact an enormous psychological toll over time. The atmosphere's composition adds another challenge. It's approximately 95% carbon dioxide, less than 2% argon and nitrogen, and only trace amounts of oxygen, about 0.16%. For comparison, Earth's atmosphere is about 78% nitrogen and 21% oxygen. You cannot breathe Mars's atmosphere at all, even if it were properly pressurized. It would be like trying to breathe inside a fire extinguisher. This means habitats must continuously generate breathable air. The most practical approach involves splitting carbon dioxide into oxygen and carbon monoxide using electricity, a process tested by the MOXIE experiment aboard NASA's Perseverance rover. MOXIE successfully produced oxygen from Martian atmosphere, starting in 2021, demonstrating the technology works. But scaling this to support human populations requires substantial energy inputs, continuously, forever. Energy becomes the lifeblood of Mars colonies. Without it, you cannot produce oxygen, recycle water, maintain habitat pressure and temperature, grow food, or operate any of the countless systems required for survival. On Earth, if power fails, it's an inconvenience, maybe a crisis in extreme weather. On Mars, power failure equals death within hours. The pressure to maintain energy systems becomes absolute. Solar power seems obvious. Mars receives sunlight, albeit only about 43%, as intense as Earth receives due to greater distance from the Sun. Large solar arrays could theoretically provide sufficient power. But Mars presents serious challenges for solar energy. Dust storms can envelop the entire planet, blocking sunlight for weeks or months. In 2018, a global dust storm killed NASA's Opportunity rover by depriving its solar panels of light. Any Mars colony relying primarily on solar power would face similar vulnerability. Nuclear power offers a more reliable alternative. Fission reactors could provide consistent baseload power regardless of dust storms or day-night cycles. NASA has developed concepts like the kilopower reactor, designed specifically for space applications. But nuclear reactors are complex, require maintenance, eventually need fuel replacement, and produce radioactive waste. Managing nuclear technology on Mars, where any malfunction could be catastrophic and replacement parts are months away, presents its own set of terrifying challenges. The temperature extremes add yet another layer of hostility. Mars's average temperature is approximately -63 degrees Celsius, but this varies dramatically. Near the equator during summer, daytime temperatures might reach a balmy 20 degrees Celsius, quite comfortable. But at night, temperatures plunge to -73 degrees Celsius or lower. At the poles during winter, temperatures drop below -125 degrees Celsius, cold enough to freeze carbon dioxide out of the atmosphere as dry ice. These temperature swings create enormous engineering challenges. Materials contract and expand with temperature changes, causing mechanical stress that can lead to cracks, seal failures, and structural damage over repeated cycles. Lubricants freeze, batteries lose efficiency, electronic components behave unpredictably. Everything must be designed to withstand temperature variations of nearly 100 degrees Celsius daily, a range far exceeding what most terrestrial technology experiences. Heating habitats in such cold requires substantial energy, further straining power systems. Insulation helps, but perfect insulation doesn't exist. Heat constantly leaks through walls, windows, airlocks, and anywhere humans or equipment pass between inside and outside. The colder the external environment, the faster heat escapes, demanding continuous energy input to maintain livable temperatures. During the coldest periods, heating demands could consume the majority of available power. The thin atmosphere provides almost no temperature buffering. On Earth, our thick atmosphere moderates temperature changes through convection and heat retention. Mars's whisper-thin atmosphere offers negligible thermal inertia. When the sun sets, temperatures plummet almost immediately. When it rises, they climb rapidly. This means habitat thermal control systems must respond quickly to dramatic changes, adding complexity and potential failure points. Water, that most essential substance for life, presents its own constellation of problems on Mars. We know water exists on Mars primarily as ice mixed into the soil and concentrated at the polar caps. The Mars Reconnaissance Orbiter and other missions have detected significant subsurface ice deposits, particularly at higher latitudes. Some estimates suggest vast quantities of frozen water lie beneath the surface, potentially making Mars less water-poor than once believed. But accessing this water requires enormous energy. You must excavate regolith, heat it to release water vapor, capture and condense that vapor, then purify the resulting water. The temperatures required to sublimate ice from frozen regolith are substantial, especially when you're trying to extract water from soil that might be only a few % ice by volume. Every liter of water represents a significant energy investment. Moreover, Martian water ice isn't pure. It's mixed with regolith, possibly contaminated with perchlorates and other minerals. Purification becomes essential but energy-intensive. The more colonists you support, the more water you need for drinking, hygiene, growing food, manufacturing, and oxygen production. The scale rapidly becomes daunting. A single human needs roughly 2 to 3 liters of drinking water daily, plus additional water for hygiene, food preparation, and waste processing. A colony of 100 people would need hundreds of liters daily, thousands weekly, millions annually. Water recycling becomes mandatory. The International Space Station recycles approximately 93% of water, including urine, sweat, and humidity from breath. Mars colonies would need similar or better efficiency. But recycling systems aren't perfect. Some water is always lost, bound in waste products, escaping during airlock cycles, consumed in chemical processes. This means continuous water extraction from Martian ice forever. You can never stop mining water, or the colony begins dying of dehydration. The recycling processes themselves create psychological challenges. Drinking yesterday's urine and sweat, purified though it may be, represents a mental hurdle many people struggle with. Astronauts joke that today's coffee is tomorrow's coffee, but the reality of perpetually consuming recycled bodily waste can be psychologically difficult, adding another stress to an already mentally taxing environment. Food production represents perhaps the most complex challenge of all. Growing food on Mars would be essential for any long-term colony because shipping food from Earth is prohibitively expensive. Current estimates suggest launching cargo to Mars costs tens of thousands to hundreds of thousands of dollars per kilogram, depending on the transportation system. Feeding a colony entirely from Earth would be economically impossible, so colonists must grow food locally. This requires creating agricultural systems in an environment completely hostile to terrestrial life. Plants need several things: light, water, nutrients, appropriate temperature, and atmospheric carbon dioxide. Mars provides only one of these naturally: carbon dioxide. Everything else must be artificially supplied. Lighting for indoor agriculture requires enormous energy. Plants need specific wavelengths and intensities of light for photosynthesis, typically requiring tens to hundreds of watts per square meter of growing space. A small farm feeding a few dozen people might need tens of kilowatts continuously, a substantial portion of total colony power. LED technology has improved efficiency, but the physics remains unforgiving. You cannot cheat photosynthesis. The soil, or rather the growing medium, presents multiple problems. Martian regolith is not soil in the biological sense. It lacks organic matter, beneficial microorganisms, and the complex chemistry of Earth soil built up over millions of years of biological activity. It contains toxic perchlorates. It has different mineral composition and pH than Earth soils. You cannot simply plant seeds in Martian dirt and expect anything to grow. Instead, colonists would need to create artificial growing media, perhaps mixing treated regolith with organic waste, imported microorganisms, and carefully balanced nutrients. This is essentially building an entire functional ecosystem from scratch, a task we've attempted in projects like Biosphere 2 here on Earth, with very mixed results. Biosphere 2, a massive enclosed ecological facility in Arizona, attempted to create a self-sustaining artificial environment in the early 1990s. Despite enormous resources, careful planning, and the fact that it was built on Earth with easy access to supplies and expertise, the project encountered serious problems. Oxygen levels dropped unexpectedly due to soil microbes consuming more oxygen than plants produced. Carbon dioxide levels fluctuated wildly. Food production fell short of requirements. The closed system proved far more complex and unpredictable than anticipated, even with Earth's gravity, atmospheric pressure, and proximity to support. Mars colonies would face similar challenges, but with additional complications of reduced gravity, no natural soil ecosystem to start from, and hostile external environment. The margin for error would be razor thin. Agricultural failure means starvation. Unlike Biosphere 2's inhabitants who could order pizza if things went really wrong, Mars colonists have no safety net. Pollination presents another overlooked challenge. On Earth, insects, birds, and wind pollinate most food crops. Mars habitats would have no natural pollinators. Every pollination would require human intervention, hand-pollinating plants, or introducing and maintaining populations of bees or other pollinating insects in sealed environments. Imagine the labor requirements: hundreds or thousands of plants requiring individual attention during flowering continuously, or food production collapses. The nutritional adequacy of Mars-grown food raises concerns too. Plants grown in artificial conditions sometimes have different nutritional profiles than field-grown crops. Vitamin and mineral content can vary based on growing conditions, light spectrum, and soil chemistry. Mars colonists would need to carefully monitor their food's nutritional value and potentially supplement their diet, adding another dependency on Earth-supplied materials. Speaking of nutrition, NASA identifies inadequate food and nutrition as another of the 4 highest priority red risks for Mars missions. Even with local food production, ensuring colonists receive adequate calories, protein, vitamins, minerals, and micronutrients represents a persistent challenge. Dietary deficiencies develop slowly, accumulating over months or years before symptoms appear. By the time you notice a problem, perhaps weakened bones from calcium deficiency or neurological issues from B vitamin deficiencies, the damage is done. The monotony of diet cannot be dismissed either. Imagine eating the same limited selection of foods grown in controlled environments, recycled and reprocessed, day after day, year after year. No spontaneous variety, no surprises. No culinary exploration. Food is not merely fuel, it's culture, comfort, celebration, and connection. The psychological impact of dietary monotony adds to the cumulative stress of Mars' existence. Now let's discuss gravity, or rather, the relative lack thereof. Mars has approximately 38% of Earth's surface gravity. This might sound substantial compared to zero gravity, and indeed it's significantly more than the Moon's 16%. But decades of research on astronauts in microgravity have revealed that the human body evolved exquisitely adapted to Earth's 1G environment, and deviations from this create serious physiological problems. In microgravity, astronauts lose bone density at rates of 1 to 2% per month, primarily from weight-bearing bones like the spine, hips, and legs. Muscle atrophy occurs similarly. The cardiovascular system deconditions as the heart doesn't need to pump against gravity. Vision changes occur in many astronauts due to fluid shifts affecting eye structure. Balance and spatial orientation become confused when the vestibular system receives conflicting signals. We don't yet have solid data on how 0.38G affects human physiology long-term because no human has ever experienced Mars gravity for extended periods. The concern is that partial gravity might cause similar problems as microgravity, just progressing more slowly. If bone loss continues even at reduced rates, colonists could develop severe osteoporosis over years, making bones brittle and prone to fracture. Elderly colonists might become physically fragile, unable to perform necessary tasks. The reproductive questions loom particularly large and largely unanswered. No human has ever been conceived, gestated, or born in anything other than Earth gravity. We have no data on whether human reproduction would even work properly on Mars. Animal studies in microgravity have shown various developmental abnormalities and reduced fertility. Would Mars gravity provide sufficient stimulus for normal embryonic development? Would pregnancy proceed normally? Would children born on Mars develop healthy bones, muscles, and organs? These aren't academic questions. If Mars colonization is to be permanent, reproduction becomes essential. But sending people to Mars without knowing whether they can safely have children there represents an ethical nightmare. And if children can be born on Mars, what happens to them physiologically? Would they develop normally? More troubling still, would children who grow up in Mars gravity ever be able to visit Earth? Their bodies, adapted to 0.38G, might find Earth's gravity crushing, literally too heavy for their cardiovascular systems and skeletons to bear. Imagine the tragedy: children born on Mars, raised under rusty skies, who can never visit the ancestral home of humanity. They would be trapped on Mars, their biology having diverged enough from Earth-adapted humans that returning would be medically impossible. They'd watch videos of Earth's oceans, forests, and blue skies, knowing these wonders are forever beyond their reach. The psychological implications are profound and deeply unsettling. The cosmic perspective here is haunting. Life on Earth evolved over 3.5 billion years in Earth's specific conditions. Its gravity, its atmosphere, its magnetic field, its radiation environment. We are, quite literally, shaped by our planet. Every cell, every organ system, every aspect of our biology bears the imprint of Earth. Moving to Mars doesn't just mean adapting to a new environment, it means potentially diverging evolutionarily, creating a separate branch of humanity physically incompatible with its origin world. Medical care on Mars presents terrifying challenges. On Earth, we take for granted the availability of hospitals, specialists, diagnostic equipment, pharmaceuticals, and surgical facilities. Serious injuries or illnesses can usually be treated, or at worst, the patient can be transported to better facilities. Mars offers no such options. The colony's medical capabilities would be whatever was brought from Earth or could be manufactured locally, a tiny fraction of what's available terrestrially. Consider a surgical emergency. Appendicitis, for instance, affects roughly 7% of people during their lifetime. In a colony of 100 people, you'd statistically expect 7 cases eventually. On Earth, appendicitis is treated with routine surgery. On Mars, the same surgery becomes dramatically more complex. The reduced gravity affects blood flow and how surgical instruments behave. The patient is breathing recycled air in a pressurized habitat. Sterilization protocols must be absolutely perfect because infection in a closed environment could spread catastrophically. And if complications arise during surgery, unexpected bleeding, allergic reactions to anesthesia, surgical errors, your options are severely limited. Dental problems illustrate the point vividly. Tooth decay, gum disease, impacted wisdom teeth, and dental trauma are common. On Earth, you visit a dentist. On Mars, dental equipment must be shipped from Earth, along with supplies, anesthetics, and someone trained in dentistry. A simple toothache could become a medical crisis if it abscesses and causes systemic infection. Extracting a problematic tooth without proper equipment and pain management would be medieval. Cancer becomes a death sentence for many. Radiation exposure on Mars dramatically increases cancer risk, as we discussed earlier. But treating cancer requires sophisticated medical technology, imaging equipment, chemotherapy drugs, radiation therapy, surgical facilities, and oncological expertise. Most of this would be unavailable on Mars. Early colonists developing cancer from radiation exposure would face grim choices: suffer without treatment, attempt crude treatment with limited resources, or accept their fate. The irony is bitter, dying of cancer caused by the very environment you traveled millions of kilometers to inhabit. Mental health treatment faces similar resource constraints. We've discussed the psychological stresses of Mars colonization, but what happens when someone develops serious mental illness, severe depression, psychosis, or suicidal ideation? Psychiatric medications help many people, but they require continuous supply. Therapy helps, but what if the limited crew doesn't include mental health professionals, or the patient cannot trust those available due to dual relationships? On Earth, you can change therapists, seek second opinions, or check yourself into specialized facilities. Mars offers none of these options. The risk of suicide in isolated, high-stress environments is real and documented. Polar research stations, submarines, and remote work sites all experience elevated suicide risk. Mars colonists would face even greater isolation and stress with no possibility of leaving. A suicide wouldn't just be a personal tragedy, it would impact the entire colony's morale and could trigger contagion effects, increasing risk for others. Yet preventing suicide in a closed environment where sharp tools, airlocks, and numerous other lethal means are readily accessible would be nearly impossible. the ethics of sending people into such danger deserve serious consideration. Throughout history, explorers have risked and often lost their lives pushing into unknown territories. But those explorers could, in theory, turn back. Ships could return to port. Expeditions could retreat. Mars colonists, especially in early missions, would have extremely limited return options. Launch windows to Earth occur only every 26 months when planetary orbits align favorably. If something goes catastrophically wrong 13 months after landing, you cannot evacuate. You wait another year, hoping your life support and supplies hold out, or you die waiting. The economics compound the ethical concerns. Mars colonization would require investment measured in hundreds of billions, perhaps trillions of dollars. That money comes from somewhere, governments, meaning taxpayers, or private investors expecting returns. The opportunity cost is staggering. The same resources could provide clean water to everyone on Earth, cure diseases, address climate change, or uplift billions from poverty. Choosing to spend that money sending a few dozen or 100 people to almost certain hardship and elevated mortality risk on Mars represents a value judgment about priorities that many would question. Some argue that spreading humanity to multiple worlds protects our species from extinction events on Earth. Asteroid impacts, supervolcano eruptions, nuclear war, pandemic, or climate catastrophe. This logic has surface appeal, but it crumbles under examination. Any catastrophe that makes Earth less habitable than Mars would have to be spectacularly severe. Even after nuclear war, Earth would still have breathable atmosphere, tolerable gravity, liquid water, and partial radiation shielding. All things Mars lacks. A devastated Earth would still be more hospitable than pristine Mars. The notion that Mars colonies could be self-sufficient enough to preserve humanity if Earth were destroyed is frankly fantasy with our current or foreseeable technology. Mars colonies would depend on Earth for countless critical supplies, spare parts, expertise, and genetic diversity for centuries, perhaps millennia. Severing that umbilical cord would doom the Mars colony, not save it. From a cosmic perspective, we must confront a humbling reality. The universe is not designed for human convenience. We are adapted to one extraordinarily specific environment, the surface of Earth during a particular geological epoch. The cosmos beyond our blue bubble is almost universally hostile to our fragile biology. We've discussed Mars extensively, but step back and consider the broader solar system. Venus, with surface temperatures hot enough to melt lead and atmospheric pressure crushing enough to destroy submarines, makes Mars look gentle. The outer planets are gas giants with no solid surface and radiation belts that would kill within hours. Their moons face similar challenges to Mars: radiation, cold, lack of atmosphere, often worse. Beyond our solar system, the challenges multiply impossibly. The nearest star, Proxima Centauri, sits roughly 4.2 light-years away. With current propulsion technology, reaching it would take tens of thousands of years. Even wildly optimistic future propulsion systems might reduce that to centuries. The spacecraft would need to function perfectly for longer than human civilization has existed, protecting fragile human bodies from radiation, providing food, water, air, gravity, and psychological well-being across generation after generation, born and dying in transit. And for what? We've discovered thousands of exoplanets, but none are Earth twins. They orbit different stars with different radiation outputs. They have different masses, atmospheric compositions, gravity levels, day lengths, and orbital characteristics. Even if we found a planet superficially Earth-like, its biochemistry would certainly differ. Its microorganisms, if any exist, could be incompatible with or hostile to terrestrial life. The proteins might coil differently. The genetic coding could use different bases. We might not be able to safely eat anything there, breathe the air despite oxygen content, or avoid poisoning by trace elements our biology never encountered. This brings us to perhaps the deepest question. Why does Mars, why does the broader cosmos present such insurmountable challenges to human survival? The answer lies in the fundamental nature of life and the universe's indifference to it. Life, as far as we understand it, is a spectacularly improbable phenomenon. It requires liquid water, energy sources, chemical building blocks, and stable conditions persisting for extended periods. On Earth, these conditions aligned for billions of years, allowing life to emerge, evolve, and diversify into millions of species filling every available niche. But Earth is the exception, not the rule. The universe operates on principles of physics and chemistry that care nothing for biological needs. Entropy increases, energy disperses. Temperatures in space approach absolute zero, -273.15 degrees Celsius, where molecular motion nearly stops. Radiation floods the cosmos, released by dying stars, black holes consuming matter, and the background echo of the Big Bang itself. Gravity sculpts matter into planets and stars, creating extreme pressures and temperatures. None of these processes consider whether life can exist in their midst. Mars embodies this cosmic indifference perfectly. It followed the same physical laws as Earth. Gravity coalesced matter into a planet, radioactive decay heated its interior, geological processes shaped its surface. But subtle differences in initial conditions, smaller size, different composition, greater distance from the Sun, led to a divergent path. The core cooled, the magnetic field died, the atmosphere escaped, and water vanished. Physics didn't care that this made Mars uninhabitable. The universe doesn't optimize for life. It simply proceeds according to mathematical rules that occasionally, almost accidentally, create conditions where life can emerge. We exist because Earth happened to fall within an extraordinarily narrow range of parameters. Our planet orbits at the right distance from a star of the right type, with the right mass to generate the right gravity to hold the right atmosphere, with a large moon to stabilize axial tilt and create tides. In a relatively quiet galactic neighborhood without nearby supernovae or dangerous radiation sources, with plate tectonics to recycle carbon and regulate climate over geological time. Change any of these variables significantly, and Earth becomes uninhabitable. This realization should inspire both profound gratitude and cosmic humility. We are, as Carl Sagan eloquently stated, a way for the cosmos to know itself, matter that has organized into patterns, complex enough to contemplate its own existence. But we're also fragile, entirely dependent on conditions so specific that we find them almost nowhere else, even within our own solar system. The dream of colonizing Mars represents a very human impulse, the desire to explore, expand, and ensure our survival by spreading to multiple worlds. These instincts served us well throughout history as we migrated across continents, crossed oceans, and settled every habitable region of Earth. But space is fundamentally different from any terrestrial frontier. There is no there that welcomes human habitation without massive, continuous technological intervention. Consider the total environmental control required for Mars survival. Every breath you take must be manufactured. Every drop of water must be extracted and recycled. Every calorie of food must be grown under artificial conditions. Every degree of warmth must be generated and maintained. The pressure surrounding you must be held exactly within survivable range. Radiation must be blocked or absorbed. Gravity is wrong and cannot be fixed. The day-night cycle at 24 hours and 37 minutes is close to Earth's, but not quite, potentially disrupting circadian rhythms over time. Nothing, literally nothing about Mars supports human life naturally. This is the fundamental difference between colonizing Mars and settling new terrestrial frontiers. When humans migrated to Australia, the Americas, or remote islands, Those places had breathable air, drinkable water, edible plants and animals, and protection from cosmic radiation. Settlers faced challenges: unfamiliar climates, diseases, hostile inhabitants, navigation difficulties, but the basic requirements for life existed naturally. You could step off the boat and breathe, not so on Mars. Step outside your habitat unprotected, and you have seconds before unconsciousness, minutes before death. Some technologists argue that sufficiently advanced technology could overcome these barriers. Perhaps future materials, science will create radiation shielding that's both effective and lightweight. Maybe genetic engineering could modify humans to tolerate higher radiation, lower gravity, or different atmospheric compositions. Possibly advanced artificial intelligence could manage the complex life support systems with reliability approaching certainty. Conceivably, we could terraform Mars over centuries or millennia, adding atmosphere, warming the planet, and creating sustainable ecosystems. Let's examine terraforming seriously because it represents the ultimate technological solution to Mars's hostility. The concept involves planetary-scale engineering to transform Mars into something resembling Earth. Various proposals exist, but they generally involve releasing greenhouse gases to warm the planet, melting polar ice to provide water and thicken the atmosphere, and introducing photosynthetic organisms to produce oxygen over time. The challenges are staggering. Recent research, including work discussed at terraforming workshops in 2026, has explored using aerogels, lightweight materials with insulating properties, to create greenhouse effects in specific regions, or dispersing iron and aluminum particles in the atmosphere to trap heat. These concepts are scientifically interesting, but the practical hurdles are immense. First, the energy requirements are astronomical. Warming an entire planet requires adding truly enormous amounts of energy or heat-trapping gases. Proposals to bombard Mars with comets or asteroids to deliver water and trigger warming would require redirecting celestial bodies massing billions of tons, technology far beyond current capabilities and fraught with catastrophic risks if even slightly misaimed. Second, the timescales are geological. Even optimistic terraforming proposals suggest centuries to millennia before Mars might have breathable atmosphere and tolerable temperatures. More realistic assessments stretch into tens or hundreds of thousands of years. This is longer than modern humans have existed as a species. Maintaining focus on a project spanning so many generations seems implausible given humanity's track record with long-term planning. Third, without addressing the magnetic field problem, any atmosphere we add would gradually escape, just as Mars's original atmosphere did. Some scientists propose artificial magnetic fields generated by satellites at Lagrange points or superconducting rings around Mars, but these remain purely theoretical concepts requiring technology and energy resources we cannot currently imagine deploying. Fourth, the ethics of terraforming are complex. If Mars harbors any indigenous life, even microscopic organisms in subsurface ice, terraforming would constitute the deliberate destruction of an alien biosphere, possibly the only other example of life in the universe. The scientific and philosophical value of pristine Martian life would be incalculable. Destroying it to make Mars comfortable for humans would be an act of cosmic vandalism unprecedented in history. The search for life on Mars represents one of the primary scientific motivations for exploring the planet. Missions like Perseverance are collecting samples that future missions will return to Earth for analysis, specifically seeking biosignatures, chemical or physical evidence of past or present life. If we find that life emerged independently on Mars, it would revolutionize our understanding of biology's universality. It would suggest that life arises wherever conditions permit, implying a cosmos potentially teeming with biological worlds. But if we colonize Mars carelessly, we might contaminate the planet with terrestrial organisms, making it impossible to determine whether any life we find is native or accidentally introduced. We could destroy or obscure the very evidence we seek. Planetary protection protocols exist to prevent this, but they become harder to enforce with large-scale human presence. Every habitat, every piece of equipment, every human body carries terrestrial microorganisms. Maintaining sterility in an active colony would be essentially impossible. From a deeper perspective, contaminating Mars with Earth life raises profound questions about our role in the cosmos. Are we entitled to spread terrestrial biology to other worlds? Do we have the right to potentially extinguish or contaminate alien biochemistries that took billions of years to develop independently? These aren't merely abstract philosophical questions. They have practical implications for how we approach Mars exploration and potential colonization. The alternative to permanent colonization, using Mars as a scientific research destination with rotating crews, similar to Antarctic research stations, seems far more reasonable and achievable. Scientists could study Mars's geology, climate, potential biosignatures, and use it as a test bed for technology without committing to permanent settlement. Crews would serve limited tours, perhaps 18 months to 2 years, then return to Earth, reducing long-term radiation exposure and psychological stress. The infrastructure requirements would be smaller, more manageable, and wouldn't demand impossible sustainability. This approach acknowledges Mars's scientific value while respecting the practical reality that Mars is fundamentally hostile to permanent human habitation. It mirrors how we treat Antarctica as a place worth studying and visiting, but not suitable for cities and permanent populations. Antarctica is vastly more habitable than Mars, yet we've collectively decided that establishing permanent civilian settlements there is neither desirable nor practical. If we apply that wisdom to Antarctica, how much more should it apply to Mars? The romantic vision of Mars cities with domed habitats, terraform landscapes, and bustling populations engaging in commerce and culture makes for compelling science fiction. Stories like Kim Stanley Robinson's Mars trilogy or Andy Weir's The Martian capture our imagination precisely because they tap into deep human desires for exploration and expansion. But fiction can afford to gloss over or solve problems with hand-waving. Reality is far less forgiving. We should honestly assess what Mars colonization would actually mean for the people living through it. Not the triumphant moments of first landing or first harvest, but the daily grinding reality. Waking each morning in cramped quarters, breathing recycled air that tastes stale, eating monotonous food grown in artificial light, exercising rigorously just to slow the inevitable bone loss, checking radiation dosimeters to track your accumulating cancer risk, managing interpersonal conflicts with people you cannot escape, performing maintenance on systems that cannot fail, and living every moment with the knowledge that you're entirely dependent on technology working perfectly in an environment trying to kill you. The psychological term third quarter phenomenon describes a pattern observed in long-duration missions where morale and performance decline most sharply around the 3/4 mark, when the mission has gone on so long that the beginning feels distant, but the end still seems far away. Astronauts on year-long ISS missions frequently experience this. A Mars mission would last years with no possibility of early termination. The psychological trough would be deeper and longer, with no clear endpoint for permanent colonists. Would people volunteer for this? Almost certainly yes. Humans are diverse, and some individuals thrive on challenge, isolation, and pushing boundaries. Test pilots volunteered to fly experimental aircraft with high fatality rates. Explorers have always accepted risk for the sake of discovery. But accepting informed risk is different from being misled about conditions. Anyone volunteering for Mars colonization deserves complete honesty about the likely quality of life, health risks, and realistic probability of survival. The commercial interests promoting Mars colonization sometimes paint misleadingly optimistic pictures, emphasizing adventure and opportunity while downplaying dangers. When companies speak of establishing self-sustaining cities on Mars within decades, they're either ignorant of the technical challenges or deliberately overselling the vision. Neither is acceptable when people's lives are at stake. SpaceX, founded by Elon Musk, has made Mars colonization central to its mission, developing the Starship rocket specifically for this purpose. The vision is bold and has driven impressive engineering achievements. Reusable rockets, improved launch cadence, and reduced costs are genuine advances, but the gap between launching payloads to Mars and establishing viable permanent colonies is vast, filled with unsolved biological, psychological, and logistical problems that rocket engineering doesn't address. The danger lies in confusing transportation capability with habitability. We can potentially transport people to Mars. The physics and engineering, while challenging, are achievable. But delivering humans to Mars is not the same as enabling them to live there safely and sustainably. It's like building a ship capable of reaching Antarctica, but having no plan for what happens once people arrive in the frozen wilderness with limited supplies. Financial sustainability represents another overlooked challenge. What would a Mars colony produce that justifies the enormous expense of supporting it? Earth-based colonies throughout history were economically viable because they extracted resources, produced goods, or provided strategic value that offset costs. Mars offers no such advantages. Mining Mars for resources makes no economic sense. The cost of transporting materials from Mars to Earth would be prohibitively expensive, far exceeding the value of any materials mined. Even if Mars contained pure platinum or gold, the transportation costs would dwarf any profit. Every element available on Mars exists on Earth or in near-Earth asteroids, which are far easier and cheaper to access. The idea of Mars as a manufacturing center fails similarly. Why manufacture anything on Mars when manufacturing on Earth has access to established supply chains, skilled labor, and customers? The only products worth manufacturing on Mars would be items needed on Mars, meaning the colony produces for itself, generating no external revenue. Tourism represents the only plausible revenue source, but the market would be tiny. The journey takes months, costs would be astronomical, the experience would be dangerous and uncomfortable, and the attractions are barren landscapes you could simulate on Earth. The number of people wealthy enough and interested enough to pay potentially tens of millions of dollars for such an experience would support, at best, a trickle of visitors, not a sustainable economy. This means Mars colonies would operate as permanent money sinks, requiring continuous subsidies from Earth to survive. Eventually, whether due to economic downturns, political changes, shifting priorities, or simple donor fatigue, that funding would be questioned or reduced. A colony dependent on external funding for survival is inherently vulnerable and unstable. The historical analogy sometimes drawn between Mars colonization and European colonization of the Americas breaks down completely under examination. The Americas had breathable air, water, food sources, and indigenous populations with whom Europeans could trade or conquer. Despite these advantages, early colonial attempts frequently failed with high mortality rates. Roanoke vanished, Jamestown nearly starved. Countless expeditions ended in death and disaster despite arriving in environments fundamentally hospitable to human life. Mars offers none of the Americas' natural advantages, only additional challenges Europeans never faced: radiation, vacuum, toxic soil, unbreathable atmosphere, wrong gravity, isolation from support, and communication delays. If colonies with every natural advantage frequently failed, what hope do colonies lacking any natural advantages have? The comparison also ignores the horrific human cost of colonizing the Americas, the genocide of indigenous peoples through disease, warfare, and displacement. We rightly view these atrocities with shame today. Mars colonization wouldn't repeat that particular horror. No indigenous people exist to harm, but it would create new ethical catastrophes. Sending people to conditions almost certain to cause illness, psychological trauma, and premature death raises serious moral questions, especially if those volunteering don't fully understand the risks. There's also the matter of informed consent across generations. Adults might choose to accept Mars's risks, but what about their children? Children born on Mars never consented to the radiation exposure, dietary limitations, psychological stress, and potential inability to ever visit Earth. They inherit risks their parents chose, but that they themselves had no say in. This creates a troubling ethical situation where one generation's choices irrevocably constrain another's options. Legal and governance questions compound these concerns. Who has jurisdiction on Mars? What laws apply? If crimes occur, assault, theft, murder, who investigates and prosecutes? Current space law, primarily the Outer Space Treaty of 1967, declares that celestial bodies cannot be claimed by any nation and must be used for peaceful purposes. But the treaty predates serious colonization discussions and leaves many questions unanswered. If a colony is established by a private company, does that company govern? Can it make and enforce laws? What rights do colonists have? Can they be expelled and sent back to Earth against their will? What if they can't afford return passage? Labor disputes, property conflicts, criminal behavior, all the messy realities of human society would emerge on Mars just as they do everywhere humans gather. But unlike on Earth, there's no established legal framework, no police force, no courts, no prisons. The isolation and small population size create conditions ripe for authoritarianism. In a colony where survival depends on cooperation and where resources are controlled by whoever manages the life support systems, power could easily become concentrated and abused. Dissenters couldn't simply leave. There's nowhere to go. The colony could become dystopian quickly, with no external authority to intervene and protect colonists' rights. Imagine a scenario: a colony administrator becomes increasingly authoritarian, rationing food and oxygen to enforce compliance, punishing dissent by reducing living space, or threatening to revoke life support access. On Earth, people could flee or call for help. On Mars, you're trapped. The closest help is months away and may not come at all. The potential for abuse is chilling and not merely hypothetical. History shows that isolated communities with concentrated power frequently develop exploitative or abusive dynamics. Communication delays exacerbate governance problems. At closest approach, Mars is about 4 light minutes from Earth. At farthest, about 24 light minutes. This means round-trip communication takes between 8 and 48 minutes. Real-time conversation is impossible. You send a message, wait, receive a response, wait again. This delay makes Earth-based oversight of Mars colonies impractical. By the time Earth learns of a problem and responds, hours have passed, and situations may have evolved dramatically. This communication lag also affects psychological well-being. Talking to loved ones on Earth becomes an exercise in delayed correspondence, more like exchanging letters than conversation. The emotional support that real-time interaction provides is lost. During crises, colonists would be truly alone, unable to receive immediate guidance or reassurance from Earth. The isolation becomes not just physical, but communicative, adding another layer of psychological burden. The cultural and social implications of Mars colonization deserve consideration. Would Mars colonists develop their own distinct culture? Almost certainly, yes. Shared hardship, isolation, and unique environmental challenges would forge strong group identity. But this cultural divergence could create tensions with Earth. Mars-born generations might resent Earth's relative comfort and abundance. They might develop grievances about exploitation if they perceive themselves as being used by Earth interests without adequate compensation. Science fiction often explores Mars independence movements, and there's historical precedent. Colonies distant from mother countries frequently developed independence movements, the Americas from Europe being the obvious example. But Mars independence faces unique challenges. A Mars colony dependent on Earth for critical supplies cannot truly be independent. Breaking away would be suicide unless the colony had achieved complete self-sufficiency, which, as we've discussed, seems unlikely for centuries if ever. Conversely, Earth populations might grow resentful of funding Mars colonies that provide no tangible benefit. Why are we spending billions supporting people on Mars when we have problems here? Becomes a politically potent question, especially during economic downturns or crises. The political sustainability of long-term Mars support is questionable, creating existential risk for colonies dependent on it. The environmental impact on Earth of supporting Mars colonization also deserves scrutiny. Launching the thousands of rockets necessary to establish and supply Mars colonies would produce enormous greenhouse gas emissions and atmospheric pollution. Rocket fuel combustion releases carbon dioxide, water vapor at high altitudes where it acts as a greenhouse gas, and various other pollutants. The environmental cost of Mars colonization could accelerate climate change on Earth, the one planet we know for certain can support human life. This presents a perverse irony, potentially damaging Earth's environment to colonize a planet with no environment, transferring resources from a world with abundant life to one that's barren. From a planetary perspective, it makes far more sense to invest in Earth's preservation and restoration than in making tiny portions of Mars marginally habitable. Climate change mitigation, ecosystem restoration, pollution cleanup, and sustainable development on Earth face enormous challenges, but they're all working with a planet fundamentally suited to life. We're trying to undo damage, not create habitability from nothing. The return on investment for Earth-focused efforts would be vastly higher than for Mars colonization in terms of human well-being and life supported. Some argue that technologies developed for Mars could benefit Earth: closed-loop life support, efficient food production, renewable energy systems, radiation protection. This is possible, but it's more efficient to develop these technologies on Earth, where testing is easier, cheaper, and safer. We don't need to send people to Mars to develop better recycling systems or efficient agriculture. We can build test facilities on Earth, in deserts, underwater, or in other challenging environments that still allow easy access and don't risk lives. The Antarctic research model demonstrates this perfectly. We've learned enormous amounts from Antarctic research: climate science, glaciology, astronomy, biology, and survival technology without establishing permanent cities there. Scientists work in difficult conditions, develop appropriate technologies, conduct valuable research, then rotate out. The same approach would work for Mars and makes far more sense than committing to permanent habitation. So where does this leave us? Having examined radiation, atmosphere, temperature, water, food, gravity, medical care, psychology, economics, ethics, governance, and environmental impacts, the conclusion seems inescapable. Mars is fundamentally unsuitable for permanent human colonization with any technology we currently possess or can realistically envision developing in the foreseeable future. This doesn't mean we shouldn't explore Mars. Scientific exploration is immensely valuable. Robotic missions like Curiosity, Perseverance, and InSight have revolutionized our understanding of Martian geology, climate, and history. Future missions returning samples to Earth for analysis could answer profound questions about life's origins and prevalence. Human missions, if conducted carefully with proper radiation protection and limited duration, could accomplish scientific goals robots cannot. But there's a vast difference between exploration and colonization, between visiting and living permanently. We can explore Mars without establishing permanent settlements. We can study it, learn from it, and appreciate it without trying to transform it into a place it fundamentally is not and perhaps never can be for humans. The distinction between exploration and colonization matters profoundly. Exploration is inherently time-limited, goal-oriented, and accepts that the destination is alien and hostile. Colonization implies permanence, self-sufficiency, and the expectation that the destination can become a home. Mars can be explored. Whether it can truly be colonized remains highly doubtful. The psychological framing matters too. When we talk about colonizing Mars, we invoke imagery of settlement, growth, and prosperity. Frontier towns becoming cities, hard work yielding abundance, challenges being overcome through ingenuity and determination. This narrative is deeply embedded in certain cultural traditions, particularly American frontier mythology. But it's a narrative built on terrestrial experience where the land itself, once reached, provided basic life support. Mars doesn't fit this template, and forcing it into that conceptual framework leads to dangerous underestimation of the challenges. Perhaps we need different language, not colonization with its implications of permanence and prosperity, but occupation, a more neutral term suggesting presence without assuming sustainability. Or even more honestly, survival experiments, acknowledging that humans on Mars would be engaged in continuous high-stakes testing of whether long-term habitation is even possible. The resources that would be consumed by Mars colonization stagger the imagination. Conservative estimates for establishing a self-sustaining colony of even a few thousand people run into trillions of dollars spread over decades. To put this in perspective, the entire Apollo program that landed 12 humans on the Moon cost roughly $150 billion in today's currency. Apollo was a spectacular achievement, but it involved short visits to a destination only 3 days away, not permanent habitation of a world months distant. Each of these alternatives would improve or save vastly more lives than Mars colonization. The effective altruism movement, which attempts to do the most good with available resources, would find Mars colonization horrifically cost-ineffective, measured by quality-adjusted life years saved or suffering reduced. This isn't to say space exploration has no value. It does, scientific, inspirational, and technological value. But there's a reasonable scale to these investments. Robotic missions cost millions to low billions, expensive but manageable. Human missions to Mars might cost tens to hundreds of billions, very expensive but potentially justifiable for scientific return. Permanent colonization costing trillions becomes much harder to defend against alternative uses of those resources. The inspirational value of space exploration is often cited as justification. Humans need dreams, frontiers, and challenges that inspire us to achieve great things. The space race of the 1960s captivated global imagination and drove technological innovation. Many scientists and engineers cite Apollo as their inspiration for entering their fields. This soft benefit, while hard to quantify, is real and valuable. But inspiration doesn't require colonization. The Mars rovers inspire millions without human presence. The James Webb Space Telescope's images inspire awe and wonder. Scientific discoveries about exoplanets, black holes, and cosmic phenomena captivate public imagination. We can inspire through exploration and discovery without the immense cost and risk of permanent Mars settlements. Moreover, there's something troubling about seeking inspiration in sending people to suffer and likely die prematurely in harsh conditions. If the inspiration comes from courage in facing adversity, we have no shortage of that on Earth. Medical workers fighting pandemics, firefighters battling wildfires, researchers working in conflict zones, activists risking their lives for justice. These people face real adversity helping others, not manufactured hardship on a barren world. The technological spin-offs argument also appears frequently. Apollo gave us Velcro, Tang, and computer miniaturization, the argument goes, so Mars colonization would surely produce valuable technologies. This is partially true but misleading. Yes, concentrated research and engineering produces innovation, but there's no requirement that this research occur in the context of Mars colonization. We can fund materials science, life support systems, and radiation protection research directly and more efficiently without the enormous overhead of actually sending people to Mars. The Manhattan Project developed nuclear weapons, but also nuclear power and medical isotopes. But we didn't need to build atomic bombs to develop peaceful nuclear technology. We could have researched it directly. Similarly, we don't need Mars colonization to drive technological development. We can fund the relevant research directly with far greater efficiency. There's also a troubling undercurrent in some Mars advocacy that views Earth as disposable or doomed, seeing Mars as an escape plan for humanity, or at least for wealthy elites. This perspective is both factually wrong and morally bankrupt. Earth is not disposable. It's our evolutionary home, a planet of stunning biodiversity, beauty, and life-supporting capacity, unique in all our observations of the cosmos. Even severely damaged by climate change, pollution, or other human impacts, Earth would remain vastly more habitable than Mars. The notion that wealthy individuals might escape to Mars while Earth deteriorates is dystopian nightmare fuel. It envisions a future where resources are diverted to save a fortunate few rather than addressing problems affecting billions. It accepts planetary destruction as inevitable rather than fighting to prevent it. This mindset is fundamentally defeatist and ethically indefensible. Furthermore, it's delusional. Mars offers no escape from Earth's problems. Those same human tendencies that create problems on Earth, greed, short-term thinking, tribalism, resource conflicts, would manifest on Mars. We don't need a new planet. We need to address human behavior and systems. Mars won't fix humanity's problems. It would simply export them to a more hostile environment. The religious and philosophical dimensions of Mars colonization also warrant examination. Some transhumanist thinkers view spreading to other worlds as humanity's destiny or purpose, a cosmic imperative to expand consciousness throughout the universe. This quasi-religious perspective treats space colonization as sacred duty, beyond cost-benefit analysis. There's something appealing about this vision, humanity as stewards of consciousness, spreading life and awareness through an otherwise unconscious cosmos, but it rests on assumptions that deserve scrutiny. Why should spreading human-derived consciousness be a priority? The universe existed for 13.8 billion years before humans appeared and would continue for trillions more after we're gone, apparently unconcerned with consciousness. Consciousness is valuable to conscious beings, but projecting that value onto the cosmos itself is anthropocentric hubris. If we value consciousness and intelligence, fostering it on Earth, in humans, in animals we're driving to extinction, in ecosystems we're destroying, perhaps eventually an artificial intelligence, seems more pressing than spreading to barren worlds. A thriving Earth teeming with diverse life and consciousness has more value than a struggling Mars outpost of a few hundred humans barely surviving. Different philosophical frameworks reach different conclusions. Utilitarian ethics, focused on maximizing well-being and minimizing suffering, would likely oppose Mars colonization given the suffering it would cause colonists and the opportunity cost of alternative uses for those resources. Virtue ethics might focus on whether Mars colonization represents wisdom, courage, and prudence, or rather hubris and recklessness. Rights-based ethics would emphasize informed consent and the rights of children born into conditions they didn't choose. Religious perspectives vary. Some see humans as stewards of creation with responsibility to care for Earth, making Mars colonization a distraction from that duty. Others see exploration and expansion as fulfilling divine command to be fruitful and multiply. These theological differences can't be resolved empirically, but they inform how different communities view space exploration. If you found this deep analysis compelling, make sure to give this video a like and subscribe to the channel. And I invite you to watch the video at the left side of the screen, Why Anyone Who Goes to Mars Will Never Come Back. In it, I explore these challenges and expand on the scientific, psychological, and practical reasons why Mars remains one of humanity's greatest challenges, and why the dream of colonization may be further from reality than we think. See you there.